In this project, we will numerically validate the data obtained by the paper named Effects of Diffuser Orifice Plate on the Performance of Air-Cooled Steam Condenser. The present 3D model is designed using SolidWorks and Design Modeler software. The meshing of the present model is done using ANSYS meshing software. The mesh type is model is hybrid, and the element number is equal to 2,668,772. Also, by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. After clicking on the porous zone tab, you can see that viscose resistance and inertial resistance values are defined as you can see in this window. After clicking on the inlet boundary, you can see that the type of this boundary is defined to be velocity inlet. By clicking on Edit, a new window will appear in which you can change the settings for this boundary. In the appeared window, all we have to set up is the pressure jump for each fan. By clicking on Edit, you are able to define this pressure jump. Now, after clicking on the Edit button in the appeared window, the most important thing that we should pay attention to is the gauge pressure, which is defined to be equal to 0, which means that the fluid flow exits the computational domain to the atmosphere. The thermal condition defined for this wall is coupled, which means that this wall is in contact with the fluid on its both sides. After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first order event and the other options available for each variable under their combo list. And for the simple pressure-velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. Now in this contour, you can easily see the pressure distribution in the middle section of our geometry and in the cases. You also can compare this pressure contour with the pressure contour provided in the paper. And in this slide, you can easily see the temperature distribution in this middle section of our geometry, which you can compare with the results provided in the paper. After that, under the surfaces section, we click on interior duct fan from 1 to 8 and then click on compute. After that, in the console tab, you can easily see the volume flow rate for each of the fans separately. After obtaining the values for volume flow rate of each fan based on the information provided by the paper, you just have to divide this value over the ideal volume flow rate, which is defined to be equal to 428 meter cubed per second. After obtaining this value for each of the fans, you can easily generate the shown graph and validate results obtained by the paper. In this slide, we have extracted the figure 1 and figure 4 of the paper, which shows a model implemented in the paper. The main purpose of designing and using ACSC systems in power plants is to prevent energy waste. In this way, these systems condense the hot steam coming out of the steam turbine and transfer the water from the distillation process to the pump section of the steam turbine. The power plant study in the present work consists of 7 rows of ACSC system. The 4th row is studied in the CFD simulation. Each of these rows of ACSC systems consists of 8 fans, and each of these fans is located under 2 diagonally porous plates. The operation of these systems is such that the hot and low pressure steam of turbine outlet passes through each of the pipes and then is transferred into the interior space of diagonal plates installed on both sides of that pipe. The underside of the pipe and the interior of the diagonal plates have a porous structure because the use of porous medium increases the contact level between hot steam and the cooling fluid. As a result, the heat transfer is increased and the condensation phenomenon is amplified. On the other hand, the air blown by the fans installed under both diagonal plates acts as a cooling fluid and causes the condensation of vapor to be faster. In fact, the fan sucks the cool in the air space below and transfers it to the plates, and the cool air is heated after heat exchange and leaves the system as hot air. In this slide, we have brought to you the figure 5 of the paper, which shows the volumetric flow rate passing through each of the fans in the model. And by using our CFD simulation data, we are going to validate this graph.
Obtain the mesh file and also the full training movie by purchasing this product.
To benefit from Mr. CFD services, including simulation, consultation, and training, contact our experts via info@mrcfd.com.